Welcome to IMAGO Tutorials. This tutorial shows how to install the latest OpenCV library, one of the most popular open source computer vision libraries, on the VisionSensor PV. OpenCV gives you a strong support for handling images. A similar installation applies for the VisionCam. Before proceeding with the installation, make sure to remove any previously installed OpenCV versions, as these may conflict with each other. Run the following command to remove the package version of OpenCV. If present, remove any previous source-based installations by running make disinstall from the corresponding build directory. Install essential libraries which are needed by OpenCV. Type the following command. When asked to continue, hit the Enter key to confirm. This command installs the Debian package development tools, including GCC and make, the Qt interface library and the high-level programming interface, which is necessary for the OpenCV video package to link properly to the latest available versions. Now let's proceed with the OpenCV installation. Create a new directory by typing the following command and move inside with cd opencv_install. Run this command next to create a repository clone of the latest available OpenCV version in the local directory. In this example, the command downloaded OpenCV version 4.0.1. This operation may take a couple of seconds. Once done, inspect the clone content with ls. Enter the only directory OpenCV via cd and run ls from there. Among the files, this directory holds the cmakelists.txt file, which is essential to generate appropriate platform-specific build scripts. Create the build directory and enter it with cd. This directory will hold the output build scripts obtained via cmake. Proceed running the following command. This command configures and generates build files for the entire OpenCV library, specifying Qt as interface language, instead of the default GTK+ interface. The ending ... specifies the location of the cmakelists.txt file, which is one directory up. Double-check the result of the configuration. The use of the Qt library for GUI must be set to yes, while the use of the GTK+ is deactivated. Before compiling the OpenCV generated builds, you may need to run this command to prevent possible errors building due to the system's out-of-memory exceptions. This operation may take a couple of seconds. To complete the trick, run mkswap/swapfile, followed by swapon/swapfile to enable memory swapping on the specified swap file. Now we are ready to compile OpenCV by launching the command make verbose = 1. The tag verbose = 1 activates the full command output, which is useful in the case of compilation errors. This operation takes several minutes up to some hours, depending on the OpenCV version installed and the features included at configuration time. A successful build ends without any errors showing up in the last output lines, as in our case. Before proceeding, run swapoff/swapfile, followed by rm/swapfile to disable memory swapping and remove the swap file. This will repristinate the initial save system settings. Run make install to finally install all generated libraries to the internal Linux folders under /user/local/lib. To allow a proper dynamic linking of the OpenCV installed libraries, we are missing just one step, namely updating the list of library directories recognized by the system. Use your favorite text editor to edit the library configuration file /etc/ld.so.conf. Add the installation directory of the OpenCV libraries /user/local/lib at the end of the file and save it. Finally, run ldconfig to create necessary links and cache to the shared libraries found in the directories specified in the file /etc/ld.so.conf. At this point, the latest OpenCV is properly configured and installed to the system and can be freely used for programming. Next, we must update our Visual Studio project configuration to include OpenCV headers and libs. We open the FrameGrabber example project which we created and configured in the previous tutorial. You can find the link to this tutorial in the description box below. Open the property pages of the project by pressing the spanner symbol and update the additional include directories in the C++ general pages. Move to the end of the line and type the following command, reflecting the headers directory of the installed version of OpenCV, in our case the 4.0.1. Also, update the library dependencies under linker input to add the OpenCV libraries. In this example, we only include the core and the image codecs libraries, which suffice for creating, reading and writing images. Finally, hit Apply to confirm the settings and OK to close the project property pages. Now let's modify the example code to additionally store the image pixels using OpenCV. First, we include the OpenCV headers to allow image reading and writing. Thus, we include core.hpp and imagecodecs.hpp. For this purpose, we make extensive use of the convenient automatic completion available in Visual Studio. Then we move down into the main function and search for the location where the image is grabbed. We then update the code block that performs grabbing successfully, i.e. no error found at grabbing time. To be able to save the grabbed image, we first need to create an OpenCV image mat, which is a specific two-dimensional matrix holding the pixel data. We specify the number of image rows and columns as the first two parameters. These values have been specified manually in the code above. Then we specify the image format. For monochromatic images, as in our case, we choose the OpenCV format CV_8UC1 that literally stands for 8-bit unsigned U single channel 1C image format. We provide the pointer to the buffer where the grabbed pixels are stored. Finally, we set auto_step to let the function automatically compute the number of bytes per row. Now that we have built an OpenCV image, we can call this function as follows to save the image on the disk with a file name. In this example, we choose the file name test.png. Notice that Visual Studio cannot recognize OpenCV definitions. This is because OpenCV is only remotely installed on the VisionSensor and locally unavailable. Nevertheless, this does not affect building and running. Hit the Run button on the top to compile and link the modified example code. If successful, the program grabs a single image from the VisionSensor and stores it as test.png. Press any key to exit as stated and exit the program by additionally pressing the key Enter. Let's open the MobiXterm established SSH connection to the VisionSensor PV and navigate to the project's executable folder, where the image has been stored. Make sure that the SFTP browser follows the terminal folder by enabling the corresponding checkbox, and press the refresh button on the top to refresh the window. By doing so, the generated image test.png appears in the window. Double-click it to open and visualize the image captured by the VisionSensor. This should visualize a clear artifacts-free picture of the scene. To improve the image, you may need to adjust the focus of the sensor. In this tutorial, we have shown how to install the latest version of OpenCV on the VisionSensor PV. We have shown how to configure a Visual Studio project to include OpenCV headers and libraries, which enabled image storing in the modified FrameGrabber example program. To see more video tutorials, check out our channel. Thank you for watching.